We have already learned about outliers. In this video, we shall learn about one extra property that an outlier may or may not have. Suppose we have a scatter plot like this. We have got 10 points and they're pretty much on a straight line, and this is the least square fit. Now suppose we add one more point, this blue point, which is an outlier because it is far from the bulk of the data. The bulk of the data is here and this point is here. And observe that the resulting fit, which is shown by the red line, has swung a lot from this black line. So because of this single point, the least square fit is now ignoring 10 points. So the 10 points all indicated that the line should be like this. Because of a single point, that line swung from this good fit to a rather bad fit position. We will call such a point an influential point. It has so much influence that it outweighed 10 points. Now observe that this was an outlier which was pretty far from this black line. So this was more or less the distance if I consider the vertical distance. Now suppose I take the outlier here. Again, this vertical distance is same. Whatever we had there, we had still the same thing. But now the resulting line is essentially ignoring this point. It is still adhering to its old position. So now the importance is given to only the bulk of the 10 points. Here we say that this outlier is not an influential point. And this example shows that the influence is not directly dependent on only the distance of the point from the original fit. So in both the cases, this distance was the same. The discussion that we are going to do in this video is based mostly on this book. The book by Belsley, Kuh and Welch. It's on regression diagnostics. You will possibly take a closer look at this book during your MSTAT days. Now, as the name of the book suggests, this discussion pertains mainly to the situation where you are in the regression setup and not in an ANOVA setup. So the inputs will be considered to be continuous. Even if there are some discrete inputs, we shall focus on only the continuous inputs. Now, whenever we do any such thing, any such fit, what we do typically is this. We have some data set. So the data set takes the form of a data matrix. It has got the various columns are the variables, including the responses and the predictors. And based on that, we get certain outputs, which are more or less these four quantities. We have the coefficients that we fit, the fitted value themselves, the y hats. So these are the beta hats, the y hats, the residuals, y minus y hat, and the covariance matrix of the coefficients. I'm not talking about the covariance structure here. I mean the covariance matrix of the estimated coefficients. That is sigma square x prime x whole inverse, that thing. So these are the four quantities of primary importance. And we will say a particular case here, all the rows are the different cases, the particular cases here, one case is influential if omission of that makes a drastic change in any one of these four things. So if you find, if I keep it or if I do not keep it, that one case, it changes the estimated coefficients a lot, that is, for example, causes the line to swing a lot, then we say that particular case is influential. Similarly for the other three things. In order to find this out, we use what is called delete one out technique. Namely, we really delete one of the rows. Suppose we take the ith row and delete it, and then again refit the entire model and see whether the resulting coefficient or the fit or the residual or the covariance matrix, the estimated covariance matrix, has changed or not, and how much has it changed. Based on that, we try to measure the influence that particular case has.